All right, guys, STAT1150. Let me tell you what's up for this week. Kind of had I had a thought, had a plan, and decided to completely go away from my initial plan. All right, we've covered the material that's required for the class, but there's actually some kind of cool and related things that had intended to cover and present and cover this week. But I've decided otherwise. I've decided to back off, present no new material, and give you an opportunity to do an assignment on. Well, it's not an opportunity; it's required to do an assignment on my math lab on confidence intervals and hypothesis testing. Let me tell you the reason I want to do that. I noticed that as long as, okay, let me back up. With hypothesis testing and confidence intervals, we've done two types. We've done for means and we've done proportions. And I've noticed, having taught this class what seems like a zillion times, I've noticed that as long as students are doing one type, they understand it. But when they get them mixed together and they're interchangeable, not interchangeable, but they're mixed together. One of the hardest things is to detect what type of test or what type of confidence interval that you're trying to conduct or trying to create based on the information provided in the problem. So anyway, long story short, what I did is I'm going to step back, no new material, and I'm just going to give you a lot of confidence intervals and hypothesis testing problem, both of proportion and means, as your next homework assignment. And again, it's required. It's not one of those not for credit. It's actually required. And really, the motivation for this is some students who have taken me over the last couple of semesters tell me that as long as the proportion problems are kept separate from the mean problems with confidence intervals hypothesis testing, that they do this just fine. But when these things are combined on the final exam, they had problems identifying which kind of test or which kind of confidence interval they were to run. So anyway, I'm doing this in hopes to get a little better scores on a final exam. There's a policy that's built into the syllabus that says if you get a higher score on the final exam than you did on the midterm, then you replace your midterm score with the final exam score. So just an example, we'll look at two. So here's it's hard to imagine, isn't it, that we're already talking about a final exam score. So, let's say that you had a bad day on the midterm and got a 48, but on the final exam you get a 92. Well, there's some conditions that are outlined in the syllabus, and you can go back and look at those. But if you meet those conditions, then you're going to get a 92 and a 92. Now, it does not work in reverse. If you got a 92 on the midterm, and you get a 42 on the final, then you're stuck with the 92 and the 42. Now, I had a student one time tell me, he said, well, Dr. Darber, that doesn't seem fair. I thought she'd lost her mind because if that's the case, what I would do if I got a 92 on the midterm, heck, I'd go to Florida. I'd go to the beach. I'd go to Mexico. I wouldn't even complete the rest of the term because I could get a 0 on this final exam. This higher score is going to trump that, so I could put a 92 there. What emphasis does the final exam have on your final score? But anyway, the reason I do this is sometimes students just don't get it the first time they see it at the midterm. But then when they see it again as the semester has gone on, they've learned more about statistics, they end up getting what I think they need to know to complete this class successfully. So that's my logic there. And actually, I think a lot of professors do that. Now, the type of problems you're going to encounter, I think this is the assignment after the hypothesis testing, but there's going to be on type 1 and type 2, and there was a video that was posted, I think, in last week on type 1 and type 2 errors and power interpretation. So you've been taught that, so there's no need for me to go back into that. But and even though you've been taught t-distribution critical values, it's something I want to go back over because students do always seem to struggle with that. Now, actually not only z, t, but I also want to look at z distribution too. So, guys, if you're conducting a t-test or a t-interval, this relies on what's called the t-distribution. And the t-distribution is a function of what we call the degrees of freedom, which is super duper easy to find. It's just the sample size minus 1. So if we were asked to find a 90% confidence interval for mu, where we have a sample size equal to 20, what would the t critical value be equal to? Well, guys, it's really easy to do because, and if you go to StatCrunch, and if you don't have StatCrunch up, just pause the video and get it up, and then just hit play. But if you go to Stat and go to Calculator and come down to T, I would do the between. Now, since we're doing a 90%, now usually we do a 95%, but I just mix things up a little bit here, up there. So I'm going to do, I need 90% of the region between the two scores because I'm doing constructing a 90% confidence interval. And I need degrees of freedom 19 because the sample size is equal to 20. So guys, the critical value would be plus or minus 1.7291. So now, we put the plus or minus there because in the confidence interval formula, we have x bar plus or minus this t critical times the standard error. And you can see the plus or minus goes with that t critical just because of the formula. Now, what if we were conducting a hypothesis test for a claim about mu? And again, sample size is equal to 20. Now, it depends, and let's just say there's a claim about mu being equal to 100. Now, depending on the way that we're testing this, the alternative hypothesis defines where our t critical is going to be located. For example, if I do a greater than test in my alternative hypothesis, that tells me that the rejection region is out to the right. So I'm looking for the t critical that defines that upper region. However, if I have h sub o mu equals 100, h sub a mu less than 100, then I'm looking in this t distribution. My reject region is down to the bottom. It's to the left. It's lower than. It's less than. So in this case, I'm going to have a negative t critical that's going to separate the reject and fail to reject region. The other option we have is we conduct a two-tailed test. And in that situation, we have a negative t critical and a positive t critical, and we have our alpha value over 2 in each. And that's not a very pretty alpha, is it? You can't even see it. So here we have alpha in each of these tails, but when we do a not equal to, we do a two-tailed test. So we take our alpha and split it and put half of it here and half of it there. So guys, for the first example, and for each of these, let's just assume that alpha is equal to 0.05. So what's the t critical for the distribution 0.05 to the right? And again, guys, we got n equal 20. So that tells me that the degrees of freedom are equal to 19. Well, guys, again, Very easy to do. We're not going to go between. We're going to use standard. Degrees of freedom 19. I want above because it's in the right tail. And I want 0.05 area in the right tail. So the T critical is going to be 1.73. All right. Now, for the other illustration that I had, really same thing, except we had a less than test. We had a one-tail test, but it was less than. So I know I'm going to have a negative T critical, and I'm going to have 5% of the region to the left of it. So guys, same thing, same degrees of freedom, but this time I want to the left, and I want 0.05 below that value. So guys, here I get negative 1.73. Now, some of you may have been screaming at me and saying, well, Dr. Darber, we already knew that because of symmetry. I understand that. But again, there's more of a point I'm trying to create here and trying to make, more of a teaching point, if you will, than just looking at this problem as a base to create a similar problem. Hope that makes sense. Now, if we have a two-tailed test, it means we've got two tails of rejection, but we're putting half of our alpha in one tail, half of 0.05 is 0.025, and we put our other half in the other tail. Essentially, I mean, if you want to go about it this way, you can get the lower of 0.025 and see negative 2.09. And we can see, therefore, I'll tell you what, guys, let me try to, we can get positive 2.09 right here to the right, again, because of symmetry. Now, you might be saying, Dr. Darber, that's contradictory. You didn't want me to use symmetry up here. This is within the same problem. If I had changed the dynamics, the sample size, the alpha value, whatever, this would have changed. But this is within the same problem. All right, now, what happens if we use a z-critical? So we're doing a hypothesis test for a proportion, say maybe 62% versus p less than 62, alpha equal 0.05. Well, guys, this type of test is called a one-prop z-test. It uses the z-distribution instead of the t-distribution. So, different distribution. This one doesn't rely on the degrees of freedom. This one has mean 0, standard deviation equal to 1. Same principles apply. Less than, my reject region is in the lower tail. The alpha value goes there. So in the z-distribution, I need to find the value that has 5% of the region to, or the area under the curve, to the left. So I'm going to use a different distribution here. I'm going to use the normal distribution. Mean 0, standard deviation 1. I want the value 0.025. No, I'm sorry. I'm doing a two-tail test, don't I? I'm sorry, a one-tail test. I was doing a two-tail, but I need to do a one-tail. All right, so negative 1.645 is the z-critical instead of the t-critical. So depending on the test that you use. So guys, we've kind of kept it simple here. There's a particular test that I didn't teach you because it's pretty rare. But pretty much for hypothesis testing and for confidence intervals, you got two types of problems that you have been taught: means and proportions. Proportions are always given identified by a percentage noted in the problem. So guys, if you're using a means problem, whether you're doing hypothesis testing or confidence intervals, both of these you're using the t-distribution. If you encounter a proportion problem, whether it's a hypothesis test or confidence intervals, then you use the z. What's the difference in the z and the t? The t is a function of its degrees of freedom. Z has mean 0, standard deviation equal to 1. So guys, I hope it's going to help. The goal is to get you guys prepared for the final exam. A lot of you contact me and you maybe miss a point here or there on an assignment and it freaks you out. You're in good company, because it would freak me out too, because I always paid attention to my grades. I think that's one reason that I did pretty well in college. But I can't stress enough that those little points here and there within an assignment aren't really a big deal. But these little points on the final exam are a huge deal, because 1, 2, 3 points on your final exam makes a lot more contribution to your final score than the 1 or 2 points in an assignment, just because of the weighting difference. One more thing, guys, I want you to see something on my math lab. Let me log in and show you some things. There's been some confusion about this, even though I talked about it in the syllabus, and I understand. That's what, 15, 16 weeks ago, and you not only have me telling you about your syllabus, you have all your professors, so I totally understand. But there's some confusion about these, like right there, there's a hypothesis testing practice problems not for credit. But guys, when I go to the grade book, and I hope I can do this without showing any grades. When I go to the grade book and go to change weights, it won't allow me to include that where you guys can do it unless I give it a point value. And see, I already see right now that should be bumped up to 20. And that should be bumped up. I'm trying to keep your midterm exam weighted about 50%, because that's kind of about where it falls. So you guys get to see exactly how I weight this out. All right, so now it's 50%. I'm going to hit save, and it'll redo the weight. But anyway, guys, the point I was trying to make before I got sidetracked is these not for credit, I've got them set at the lowest level credit that my math lab will let me set them. But if you're not doing those things, fine. Again, it's not for credit. And what I will do is I'll go in and eliminate these completely from your grade calculation in the very end. So right now, if you're not doing them, they have a little bit of an impact, but very, very, very little impact on your final grade. But in the end, they won't have any impact whatsoever. Now, the quizzes will. Those sneaky quizzes do have an impact. So, guys, I guess I've covered what I wanted to cover. Only one video this week, so that should kind of make you happy. I'm sure you're probably getting sick of listening to me, and you're probably getting sick of looking at my hand. So I had a student in the other day, and she was like, Dr. Darver, I don't think I would have known you if I met you on campus, but I think I would have known your hand because I see it so much. So, guys, I hope you had a great Thanksgiving. And if you're taking this class in a future semester, you're like, well, Thanksgiving was a year ago, but or 6 months ago, whatever. It doesn't apply. But for the people taking my fall 2017 STAT1150, I hope you had a great Thanksgiving. Give you a little bit of time to kind of regroup and re-energize, because, guys, final exams are coming up soon. Speaking of final exams, there's going to be information. The the way it stands right now, the final exams must be proctored, so you're going to have the option of being proctored through ProctorU. You'll have to go in and set up an account, and I'll show you how to do that. You'll have to have a computer with a webcam. If you don't have one, see if you can borrow one. And if you can't make any of that happen, you're going to have to come to campus, and it has to be in a proctored environment. So, sorry for that news, but that's just the way it is. Well, guys, that's all I got. Again, I hope you're doing well. Take care. Happy studying.